So this is a short discussion on the material in section 5.2. So we're going to be talking about the area bounded between a curve and the x-axis and how we can calculate that. So in this section, we're just going to use geometry to do that. In the next section, 5.3, we're going to be using antiderivatives. Okay, so let's just introduce this notation here. So the area bounded between a curve, like a function f of x, and the x-axis from A to B is this integral thing that looks, thing that looks like an integral. So we talked about antiderivatives in 4.9, and so now this is a definite integral. So the integral from A to B of f of x represents the area between the graph of f of x and the x-axis. So, and if any of the area is below, the area above the x-axis is going to be positive. Any area below the x-axis will be negative. So like here, this first example, all the area from A to B, the total graph from A to B is above the x-axis, so all that area is positive. And then the second example right here, yeah, so the area from, then wherever this x-intercept is, so part of the area is positive and part of the area is negative. And if you wanted the total area, you'd have to take the positive area and subtract off the negative area. Okay, so let's actually, so for right now, we're going to evaluate these definite integrals just using geometry. That's section 5.2. So let's look at this first one right here. And so it's the integral. I can make this a little bit bigger. I changed my mouse so I can actually see it. Okay, all right. So yeah, so we're gonna find the area under the curve y equals x plus 3 right here from -2 to 1, and we're gonna break it up into two geometric shapes, a rectangle and a triangle, right? So when x is 1, right, the total height is 4, right? This point here is 1 comma 4, and then the base from -2 to 1 is 3. So let's just go up 1. Okay, so you have this triangle whose you have this rectangle whose dimensions are 1 by 3. Here, I'll just kind of shade that part in right there a little bit. And then the triangle is, well, the height there is 4 minus 1 or 3, and the base is 3. So the area of the triangle is 1/2. I kind of circled it already. 1/2 3 times 3, and then the area of the rectangle is 3 times 1. So the total area of the part that's shaded in yellow is 15/2. And yeah, we're just gonna denote. So this what I had this integral, this definite integral from -2 to 1 of x plus 3 dx. That's our notation for that area under the curve. Okay, so when you see this, that means area under the curve from this lower limit to the upper limit. So in this case, it's the area under the curve from -2 to 1, and that's a lot of what calculus is about, is evaluating these definite integrals. You'll definitely see that a lot in calculus, Calc 2 and Calc 3. Okay, so let's look at this other one. Okay, let's compute the area bounded by the graph of 2x minus 1 from -1 to 3. Now, part of the graph goes below the x-axis, part of it goes above. Okay, so now you have to be careful, because first time I looked at this, I did this wrong. It's where is it intercepting the y, the x? What is the x-intercept? So you solve 2x minus 1 is 0, and it's x equals 1/2. So you have these two triangles, okay? But so here it goes from -1. So the first triangle goes from -1 to 1/2, and then the second triangle, the base goes from 1/2 to 3. Now the height of the second triangle, you plug in 3, you get 5, right? And what's the height of the triangle 1? You plug in -1, yeah, you get, well, it's -3. But the distance is 3, right? You're going down 3. Okay, so this first triangle, the one that's below the x-axis, so the height is 3, the base is 1.5. You multiply that by 1/2, you get 2.25. Okay, for the second triangle, because we're going from 1/2 to 3, so the base is 2.5, the height is 5. Multiply that together, multiply by 1/2, you get 6.25. So now this definite integral here, the area under the curve, the area bounded by the curve of 2x minus 1 and the x-axis. So it's the positive area minus the negative area. So the positive area, that's the one above, part above the x-axis. So that's area 6.25. And you subtract off the negative area, which is 2.25, and you get a total net area of 4. Now, if you actually wanted the total area, yeah, you'd have to break this up into, well, we did break it up into 2 parts. But we're going to learn in the next unit how we can just do this all in one piece. But if you actually wanted the total area, you'd even have to break the method I'm going to show you we're going to learn in the next unit. You're going to have to break up into pieces if you actually want the total area. But the net area is 4. Everything above the x-axis minus all the area below the x-axis. So, and so that's a lot of what you're going to do in this unit here. So like here's one, the integral. So this one, right? Let's just do one more. And I have a couple problems that I did from the homework. Like okay, so the integral a. So the integral from 0 to 5 of 2. So that's the area bounded by y equals 2 and the x-axis from 0 to 5. Yeah, and you see that's just a rectangle. So the area is 10. The base is 5. One dimension is 5. The other is 2. You get 10. And I think you can do some of these other. It's all just rectangles. Well, here's 1D. We kind of like this one, and that's okay. The integral from 0 to 4. So that's just a 1/4 of a circle. Okay. So right. Y equals the square root of 16 minus x squared. So that's x squared plus y squared equals 16. So that's the circle whose radius is 4, centered at the circle, centered at 0, 0. And so, so you're just taking actually 1/4 of that. So the area of the whole circle, right? If the radius is 4, the formula is pi r squared or pi times, it would be 16 pi. The whole circle would be 16 pi, right? Oh, here it is. So that's our. So the whole circle is represented by that equation, and we know the area of that circle is 16 pi, and so we just want the area of 1/4 of that, so we get 4 pi. Okay, sometimes you see this kind of problem come up in calculus, so it's kind of good to know that trick. That's really just the area, but that's just the area of a circle or part of a circle. Okay, so let's just look at. Okay, so let's just look at this right here. A couple of things we need to know. Okay, so if the integral from a, like the area bounded from a, you're not going where it's just 1 point, a to a is 0. Here's something that's kind of important. I say kind of, I guess. I shouldn't say kind of. Either it is or it isn't. It's important, okay? See how we're going integral from a to b, and now we're just changing the limits. We're putting the a goes at the top and the b goes at the bottom. You just change the sign. So the integral, the area under the curve from a to b of f of x is minus the area under the curve from b to a of f of x. Okay, so let's say you multiply a function by k. You can actually just evaluate the integral, the area under the curve of f from a to b, and then multiply by k. Okay, so let's say you're estimating you're finding the area of a difference, f of x minus g of x, or a sum. You can actually break the areas up into 2 pieces. If maybe sometimes that trick is really quite useful. And here's something that's really very important right here. So the area under the curve from a to b, let's say c is, it's kind of nicely illustrated here. The area from a to b, let's say c is in between a and b. So first we can actually just find the area from a to c, and then find the area from c to b. So we can actually break an integral up into 2 pieces. Okay, so and then you see these kind of problems. I think in you see some of these in my lab. Okay, you're just told that the area under the curve from a to b is 5. From a to b, the area under the curve from a to b of f of x is 5, and the area under the curve from a to b of g of x is -3. So then you kind of have like this problem. Let's just do one of these. So what is the area under the curve of 2f of x plus g of x? And then we'll just use these rules. First, we break it up into 2 pieces, right? And then we just pull this constant 2 out. So and we're told that the area under the curve from a to b of f of x is 5. And we're told that the area from a to b of g of x is -3. So we just add it all together. 2 times 5 plus -3 is 7. So I think there's at least one or two problems like that in my lab. So I think the others are really pretty straightforward. So let's actually just look at let's just look at one of these problems right here. So hello. Okay, so let's just look at this problem right here. So let's find let's just let's find the area bounded by the graph of y equals 2 minus absolute value of x from -3 to 3. So first let's find the graph. Well, we know that the graph of minus the absolute value is just this upside down v, and then we're going to add 2. So we're just going to shift the graph up. So it has to be well, it can't be A and B because it's an upside down V, and in this case we're shifting it up to. So it has to be this graph right here, and so let's see here. So and if you want to find that, no, we're just going to have to break up. Let's look at the graph and break it up into appropriate pieces. So we're going from -3 to 3. So in this case, it was broken up into three triangles though. Triangle 1 and triangle 3 actually I think have the same area. Okay, so where does it intersect? So the height of, so let's just look at rectangle 2. Okay, so where are the points of intersection? So on the y-intercept, this point here is 0, 2. And so in x is, so we're actually looking, remember the graph of the function is, okay, so it intercepts the x-axis at 2 and -2, right? So -2 comma 0 and 2 comma 0. So let's just look at this area 2. So we know that the base is 4 and the height is 2. So the area of the part above the x-axis, the area is 1/2 times 4 times 2. And let's look at the part that's under the x-axis. So we're told we're going from -3 to 3. So from the x-intercept, -2 to 3 is 1, or the x-intercept 2 to 3 is 1. And when you plug in 3, it's an even function. So when you plug in x equals 3 or -3, you get the same number. So you're going to get it's going to go down to -1. Oh, this should be a -1 here. Okay, so and so the areas of triangles 1 and 3 are the same. So it's 1 time base time the base and the height are 1. And you multiply it by 1/2. And so we just use this for, area of triangle 1 is 1/2. Area of triangle 2 is 4. Area of triangle 3 is 1/2. And so altogether, the total, I meant the net area is 5. I'm sorry, that's the total area. The total area is 5. I'm sorry. The total area, right? We're not subtracting off the negative areas, right? So the total area is 5. That's my fault. So the total area is 5. The area bounded by the graph of y equals 2 minus absolute value of x, and the x-axis is 5. So we just added up the area of these 3 triangles right here. Now, what's the net area? It's the triangle above, it's all the area above the x-axis minus all the area below the x-axis. So it's triangle 2, the area of triangle 2 minus the area of triangles 1 and 3. Right, so that's what we did. So the area of triangle 2 is 4, and the area of triangle 1 and 3, they're 1/2 each, so it turns out to be 3. It's pretty interesting problem. And then, so we have to be good at triangles, rectangles, and circles, but okay. So should we do one more? Oh, do you see the cursor? What happened to the cursor? We'll see the tape. Yeah, I just changed the cursor because I couldn't find it. I wonder if I made it too big. Anyway, I didn't know you can make the cursor bigger or change the color. I've had this computer for years. Okay, so anyway, that's really why I'm doing this video, so I can talk about my cursor. Okay, so okay, here's another one. We want the integral, see this expression right here. So this is, I think, problem 12. So that expression, pi to 2 pi x sine x, and I don't think we learn how to evaluate that this semester, but next semester, that's something to look forward to. You'll learn how to get the, I think, the definite integral of x sine x. And So, okay, so x sine x, okay. Okay, so if you look at this graph right here, well, here's pi, and here is 2 pi right here. So, and so we just want all the area bounded by the curve and the x-axis. So, so if you actually evaluate that, because remember the definite integral, this expression right here, what we call the definite integral. So anything below the curve is going to be negative, right? And they're actually giving us what those areas are below the curve. They give us some information which isn't really important for this problem. We don't really need R1 or R2, right? This blue part here, or see, they tell you R1 is 1, and they tell you R2 is pi minus 1. We don't really need that for this problem. All we need is R3 and R4. So we'll throw R1 and R2 away for now. Maybe we'll see R1 and R2 again someday in another problem, if we're lucky. Okay, so all we do is we add up the area of R3 and R4, and R3 is pi plus 1. The area of R4 is 2 pi minus 1, and you add them together and you get 3 pi. Right? So the area, so this total area here, R1 plus R3 is 3 pi. And then the definite, but because it's below the x-axis, the net area is negative 3 pi. And I think that's it for this problem right here. So let's see, I'm going to stop the video.